Everyone, it's Sakai, and today we're going to be breaking down the severe weather setup in Nebraska and the high plains in the Midwest, and we're going to be talking about the tornado risk today, which is really interesting because it's a 15 hatched risk, but it's only CIG1, not CIG2. So, well, why is that? Let's go into it. First, we'll start with the live observations, and you can see this is the latest surface map for 9Z today. And the culprit for today's severe weather event is going to be this diffuse area of low pressure. And this low, it's slowly going to move to the northeast, and the moisture is going to surge northward and become unstable as the day goes on. Let's look at the current satellite presentation. I can take a new one real quick. So let's go low zoom factor and just click somewhere over this area. This is a wonderful site when it comes to satellite. That is where I get a lot of our stuff from. You can see we have a ton of elevated convection up here, but that's north of the warm front. But you can see that Nebraska, and critically the main risk area, the southern half of the main risk area, especially eastern Nebraska, is quite clear and quite unstable. There's still a lot of clouds further north where the front hasn't lifted yet and where the dry air hasn't gotten to yet. But you can see that the dry air is coming in and punching through this area. So that dry slot is slowly making its way northeast, and we'll see how quickly that can get to this area of the warm sector and how that destabilizes. Let's start by looking at the HRRR. So we're going to start with the convective evolution. I do start with convective evolution on HRRR for one reason, because if you click on a convected set, like if you're looking at a dew point map and you're like, oh, it looks really cool there, I'm going to click, and then you don't know if you're clicking on a storm or not, and you'll get a unrealistic sounding. This looks pretty realistic, but if you go back on composite reflectivity, you can see I clicked literally like right there. That's like a bit too storm influenced for me. So you can see at first glance that like we have a big line that forms in northern Nebraska and South Dakota, and it moves east into the area, after which at about 22 to 23 Z, more storms go up along the dry line. Like you can see a row of broken storms form up, and it expects them to quickly go upscale. There's some attempts at convection in Kansas which are like not super duper solid, but there is some supercellular convection over there as well as some scattered convection in Minnesota and northern Michigan before everything squalls out overnight. So what is going on here? Let's see if we can get better zoom. Unfortunately, you really can't get a better zoom to work with this because that one goes too far south. And then the only one over here is, kind of too far north. Actually, no, this is pretty good. So we're going to work with this view over here. Let's look at the upper dynamics. So you see the 500 millibar trough. It's not exactly the most eye-catching thing. Actually, HRRR has way too many artifacts, so I would rather look at something like this on RAP, which is not as heavily, convectively influenced. So let's see this. Yeah, you can see the trough. There's definitely trough over here. It's not the strongest at 500 millibars, and this trough's kinematics are much lower based. They're bottom heavy. But if you look at 700, you'll see a different story. If it'll load, you can see we have a pretty strong 700 millibar jet. I'm going to switch my view again so we can see the jet better. We have a strong 700 millibar jet coming through this area and you have a little bit of a speed max over eastern Kansas, Nebraska, and Iowa. In kind of this area, and you have another burst of it over here in Minnesota, near where the warm front and all that stuff are. So there's definitely some support there. Usually you want to look for a 700 millibar jet combined with like where strong and healthy surface moisture is located. That I found to be pretty helpful in predicting initiation. And you can see that the 700 millibar jet overlaps best with strong moisture in this area. So I would be most confident in surface-based storms happening somewhere in this area. Let's go to surface convection so we avoid clicking on a storm or something. So if you get a sounding here, it should be pretty solid. And you can see the instability profile is pretty solid. You got dry air up here, so it's probably going to prevent crapvection, and this is going to be a big factor in inducing the hail risk. However, when I look at the sounding, although you see good curvature and this is tornado, my mind initially goes hail and wind. Why? Well, look at the wind, look at the dynamic instability aloft. It's not that strong, only 35 knots SFC to 6, 41 SFC to 8. There's not enough, there's not enough dynamic instability, which is a fancy term for strong winds aloft, which is what this shows, to vent out the updrafts properly. So your risk of updrafts going outflow dominant or like having downdrafts that collapse back on themselves and getting slop or kind of disorganized storms is quite high. And those type of profiles tend to favor, hail, downbursts, or like heavy winds and stuff like that. So initially, although tornadoes could happen, because we don't have strong dynamic instability, I would be pretty dead set on a hail and wind threat today. Now let's look at the tornado parts of the sounding. However, you look at the photograph, it's pretty good. It's pretty streamlined near the surface. You have 35 knots, you have 160 knots of SFC to 1 kilometer SRH, which is not surprising because this is higher altitude. But you have 281 of effective inflow. The storm is using a lot of this. Most of the wind shear from the SFC to 3 kilometers is being used by the storm because it is very, very streamlined here at the surface. So at the surface, you do have good low-level shear for tornadoes. You have great 3 cape, lots of lower-level surface instability, and you have pretty good lap surge as well. But above that, you would be kind of hard-pressed to get a tornado. You do have good instability to offset weaker dynamic instability, but still the weaker dynamic instability is going to be a problem for storm organization. Storms will probably struggle to, organize directly in a tornadic sheared fashion, but you never know. A merger could go right, something else could go right, but bottom line, I would be more confident in hail and wind than tornado, but tornado is especially not impossible. Let's look at the upper level dynamics, see what type of initiation vectors we are working with. Let's go to 500, open a new tab. We're going to go 850, open a new tab. So 500, 850, let's look here. This is the area we have identified as the high risk area. Best 700 millibar max, best dew points over here. You can see right here that there's it's not a huge change. It's like maybe, a 30-degree change. That would make me think more semi-discrete in a linear mode. This is the reason why HRRR ends up with that type of output. As you can see, things start there, elevated, then they move into the surface-based area. You get some discrete initiation initially, but before everything, kind of congeals up and goes linear. However, there is a big problem here when it comes to, tornado odds, especially if you're looking for more isolated, long-track, higher-end scenarios. The dry line, as you can see, that is a terrible view. Let's go further south. The dry line is kind of oriented north-northeast to south-southwest, and I've seen from my experience that initiations and lines that form with that type of orientation that move east really don't produce tornadoes that much, because if they're moving east, the inflow from the storms up here, or the outflow from the storms up here, goes down and shunts the storms further to the southwest. So you will rarely ever see lines with this orientation produce tornadoes. I have seen some do so before, but basically that only happens if there's one area in the line that isn't tilted like this, but is rather straight. You have an embedded supercell that does that. That happened earlier this year in Illinois. Or the line is moving this way, or the line is moving southeast, so the outflow can't get in front of the storm. But this line is doing neither. It's moving northeast, but dry line also, it's moving east-northeast, but the dry line has that outflow favorable orientation. So I'm not too certain about QLCS tornadoes. However, it's absolutely not impossible. Why is it not impossible? First of all, along the line, there's tons of forcing, and we have tons of instability today. We've established that. You click a sounding here, you have tons of instability, and you have tons of ML cape instability. Sure, it's getting stable to surface, but this is a line and nobody cares. So definitely that instability at play today could overcome the unfavorable outflow at the surface. Second, look at the lower level jet photograph. The SFC to 3 kilometer SRH value is 491 knots. The lower level jet will be really, really strong this afternoon. And those two factors could easily overcome the unfavorable line orientation. And this is definitely, with these type of shear profiles, I would be pretty surprised if all you need is in the Omaha area, around this area, to get a solid embedded supercell with any form of a northerly orientation. That should easily be producing QLCS tornadoes, and I think something like that would have a risk for a strong QLCS tornado as well. Like this feature, for example, don't actually take this literally, but if you get a feature like this, where there's a north-southerly oriented part of the line, watch that for QLCS or significant tornado potential later today. That is why I assume that they're so confident in tornadoes happening here, but they're not SIG-2. There's just so much lower level shear here that you cannot ignore it. Now, let's look at the more conditional risks, or the better risks for, tornado activity. First, let's look at the map. You always go to the warm front. Why do we care about warm front? This warm front should jump out to you right away. Well, let's look at the laws of physics. A warm front is right here, and a warm front separates colder, denser air up here from warmer, lighter air down here. When warm, light air moves north into the cold, denser air, because this air is denser, it forces this air up, creating lift here locally around the warm front. So there you can see that there's some convective activity going on. Second, because of the wind shift that's almost always present, wrong map. At the warm front, like lower level shear here would probably be higher than it is anywhere else. Like you can see here. Actually, no, I clicked on a storm. Dang it. Okay. Yeah, here. This should be good. Yes, you can see that there's much more directional shear here, and there's a much more lower level shear here. These profiles honestly do remind me a tiny bit of Valonia, but definitely nowhere near as strong, or they don't have as much shear, where right along the warm front, you just have so much more directional shear. So shear here is better for tornadoes, and also there's more moisture, more low-level instability, but it's just a game of hit or miss as to whether a supercell is going to form here or not. However, if you do get a surface-based supercell here in the warm front in this area that manages to stay surface-based and not cross the warm front and be elevated, that should have a pretty good tornado risk. Yeah, look at this. Look at it later on. As the LLJ gets stronger and we click that warm front area right here in that triple point area, look at that profile. Incredible lower level shear, tons of directional shear, and still tons of instability aloft. If you can get a supercell there that can drill through that stable layer, you will absolutely be seeing some form of tornadic activity. Will it happen? That's a toss-up. But if it does, watch that area for significant, longer track, maybe higher end tornadoes. But it's conditional. No guarantees. Further south in Kansas, we also have some initiation, so let's take a look at that. See why it fires. So stuff does go up in Kansas later on. And you can see like some of the soundings here, but I think model consensus is that it's drier. Actually, that might not be the case. It might just be HRRR's terrible dry bias. So let's check. Okay, dang, it is pretty dry down there. Down in Kansas, you do have more initiation, but like, I mean, let's go to NAM, because like, remember how I said earlier, NAM's 700 millibar jet handling is pretty good, so let's consult that. It does have a 700 millibar jet in Kansas. Is there a newer run? It has a pretty solid 700 millibar jet in Kansas, but let's look at how that lines up with moisture. Like, it lines up pretty well. I think that's inflated. That's inflated, but it is consistent with a 700 millibar jet. But still, like, there's usable dew points, and there's a 700 millibar jet, which NAM handles pretty well. RAP has always never been consistent with, has always been conservative with jets. So let's look at HRRR. And you can see there's components of a surface jet down there. So if the surface jet, well, not surface jet, my God. If the 700 millibar jet is as strong as it seems in Kansas, look for storm initiation to happen there. However, storms there will be battling just drier air in general because of the advection regime. What do I mean by that? You can trace the wind barbs. So the stuff, like, first of all, there isn't strong winds aloft over Kansas. Like, the 500 millibar jet is stronger up here than it is down in Kansas. And you trace the wind barbs, the air being advected aloft into this part of the warm sector is pretty dang dry. It's coming from Arizona and the Texas Panhandle, which are two places that are not exactly known for being dry. So I would expect storms here to maybe be a bit more isolated, but also struggle with being outflow dominant. And I think storms here, any storm that goes up here, it's definitely high risk just because it's drier and there's less kinematic support. So I would vouch on anything going up here to kind of go blob mode and go slot mode and go outflow dominant and not do too much. Not impossible though. You do have pretty decent like lower level jet photographs, but like the dry air and thermodynamics are too negative for me to pay attention to that. The last thing we're going to cover in this video is the MCV risk in Michigan, which I know was just highlighted by the SPC. See if there's a newer run out. There is. Okay. Yeah, look. If you get a supercell right there along the warm front that is south of the warm front later on, when the LOJ goes up, that can remain isolated, watch out for that. But another thing just working against Kansas is also it's super dry, and remember the orientation. The northeast component of the dry line here there is more advanced. So any storm that goes up there would just get shunted on by unfavorable alpha. Let's look at the MCV risk. There is shear there, but I'm low-key not seeing the vision based off of that. It's not good to consider one model. Like, surely they must have seen something else. Okay, here it's better around this time. Let's take a look. There is like decent shear there. Like that kinematic profile is not bad at all. It's pretty streamwise, but it's a bit lax. I'm not entirely sure. There is a strong 700 millibar jet over that area, and we can see where the 700 millibar jet and the moisture overlap. They do overlap in this area. So let's take a sounding from here. This is why you don't consult one model. Although it's kind of disorganized, you don't have much convective instability, you don't have much dynamic instability because the winds higher up are weak. You still have a pretty big lower level shear profile. And like you have a strong 700 millibar jet. Definitely, if you can get any convection up in this area, I'm just doing that to avoid convection. Well, not up there, but it would have to be higher up here, near the front, that can go up and be surface-based. Watch out for that for sleeper tornado potential. So, to summarize, we have 4 main areas. One over here. The chance of you getting a discrete supercell is not as high, but if you do get an embedded supercell with a favorable line component, or a north to south line component, or just any well-established embedded supercell, the LLJ and moisture here and available instability should be able to offset it significant tornado risk. 2, high risk, high reward. If you get a surface-based supercell here in Minnesota, southern Minnesota, along the warm front that can stay surface-based later on when the LLJ ramps up, significant tornado risk. 3, Kansas. The dry line orientation here is very unfavorable and favors a lot of outflow. Also, it's drier, but I mean like non-zero chance, but stuff here should go severe, but I would expect it to blob out. It's more likely to blob out than go majorly tornadic. Not as big of a threat. And 4, Michigan. Michigan's the wild card. You have the strong 700 millibar jet aloft, but there's a very small area where things could happen. Just look for like about central Michigan, like maybe the area north of Grand Rapids, Hudsonville, this area, where it is paired with that 700 millibar jet. If you get a surface-based supercell there, there's definitely a tornado risk, but that's just uncertain. But, you know, if we get a tornado warning over there later, I would pay attention to it. So that's all, folks. Thank you so much for watching this breakdown, and that's what I think is going to happen today. Most likely to get tornadoes this area with an embedded supercell, but highest risk for an intense tornado up here by the warm front. Thank you for watching.